Hello, and welcome to the stream. Hopefully everything is working correctly. I say this every time now, but hopefully the audio is working okay, and if it's not, I'm sure someone will let me know. Alright, so let's actually just dive right in today because I wanna cover some ground, and I don't want to rush. Um, yeah, and I just want to make some good progress. Some really cool stuff today, I hope. So I want to do a little recap just in the beginning to get up to speed. In the last like 5 or 6 live streams that I've been doing, I've been building up a kind of driver stack and a whole hardware interface thing in Node, in TypeScript specifically, but for Node. And this is allowing us to talk to different kinds of hardware devices, and one of those is an SD card. And so over the course of the last few streams, we've been building up this SD card driver stack, which starts over here with a computer. We talk to this device called the Bus Pirate, which, if you're not familiar with it by now, well, I'm not sure how much of this will make sense, but I will show it in a minute. So the Bus Pirate is a device that can kind of take messages that you've sent over USB. In this case, we talk through a serial port over USB to the Bus Pirate. The Bus Pirate can take those messages that we send it and convert them into different kinds of serial buses that like other devices can connect to. So some of those include like I2C and OneWire and SPI. And in this case, for the SD card, we're speaking this over this protocol called SPI. So we speak from the computer, we send messages to the Bus Pirate. They actually go over the physical layer of UART and over USB. They arrive in the Bus Pirate gets them kind of ready and speaks then on our behalf, SPI, and those SPI messages, they go across to the SD card, and then the stuff that is on the SD card is just pure data, but it happens to be a file system, and then we can through the process of talking to the SD card, we can actually talk to the file system and get files from it and write files to it and delete files and all of that kind of stuff. So sort of in the last stream, we began to do some stuff with the FAT32 file system, and we got all the way to reading a file from the file system, but we didn't really kind of get a full understanding of what's involved. I skipped over a lot of things just because I knew that we needed to lay some ground. And today what I want to do is I want to get to the details. So I want to talk about the data structures that are involved in FAT32. I want to talk about like how we can read a file but properly, because before, the file that we read just happened to be small enough so that it fit into one physical block of the SD card. But what happens if your file is bigger than that? If it's bigger than 512 bytes? In that case, you somehow need to work out where you're going to get the rest of the data from, and it's not immediately obvious. So that's one of the big things that we're going to be doing today. And I'm actually really excited about it. I've got one more like kind of little diagram just to really drive this home. This is kind of what we're building. And at the bottom here, we've got this Bus Pirate driver. I'll just quickly show the Bus Pirate. Also, to show off the new camera, hopefully you can see that the new camera is a little bit better quality than my previous camera. And what I'm hoping as well is that the autofocus will serve me a little bit better. So I'm hoping that, yeah, that looks like it's probably getting it. This is the Bus Pirate. So you can see that there's USB on this end. That's where our data goes in. It goes kind of through these two chips here, like kind of actually in that order. And then it comes out of these wires and goes into other devices. And in this case, it goes into this bundle of wires that I have with an SD card attached at the end. And that is literally basically just wiring into the physical pins of the SD card. So if you turn an SD card over on the back, there's actually these little metal strips. They're electrical contacts, and we're wiring directly from the bus pirate into those contacts. So now, with that in mind, what we're actually building here is a kind of driver stack. So at the bottom of the driver stack, we have the bus pirate driver. This is like just the basis information that we need to send to actually get this device to turn on and recognize and like be able to control its basic functions. That's the base level driver. On top of that driver, we can then begin to write an SPI driver, and that is so that we can specifically describe the commands and the different things we need to do for the SPI data bus. And once we have that driver in place, we can actually then write the SD card driver, which builds on top of that again. So we're actually building on top of each layer as we go. And then those things together, they kind of form like a block device, you can think of it. It's one thing that it can form. So in this case, basically, if you put those things together, and if you do the things that we're going to do in the next, the autofocus is much better than it used to be. It's definitely an improvement. So if you put these things together, you can make a block device. And a block device is basically something that you can read from, something you can write from, and you read and write in blocks. So we have to read and write 512 bytes at a time. That's just the way it works on these devices, especially in flash technology. And what we can actually do is kind of abstract the SD card away, because a file system can be built on top of any physical storage, right? So we kind of want to just treat this driver that we have as kind of a generic storage medium. And then we can build a layer on top of it, which is a FAT32 file system layer. And that layer can potentially talk to different kinds of storage media. So what we might do in the future is like maybe talk to some other kind of device and implement the same interface as the SD card, which is just read and write, basically, read and write a block. And or we could actually just write some code that reads and writes from, an array or something like that, and then we can still plug that into the FAT32 file system layer. All right, so with that kind of introduction done, let's hit the code, because we're going to have to write some code today. All right. So the goal today is to understand, and understand is the main thing, right? Because we're not going to be able to cover everything, but we should be able to understand how the practical things that we do today, like how the rest of those operations are going to work based on that. So the first thing we're going to need to understand is the FAT. We didn't even touch on this last time, but the reason this file system is called FAT32 is because at the kind of very center of it, there is a data structure called the file allocation table, and that is kind of the secret source of how we are going to like know where our files are and how we're going to read them, and like kind of any extra kind of information about the files themselves that isn't just what directory are they in and kind of what is the size of the file. We're going to talk a little bit deeper about clusters and sectors and kind of how that works in the context of the SD card. And we're going to talk about reading and writing files, but arbitrarily. So any size of file, any type of file, to any directory, how we could potentially add new directories, how we can delete things as well. That's also an important point. And that's the goal for today. If we can get this done, I'll be really happy. And the first thing that I want to do is to actually go and generalize the device interface so that the FAT32 class can potentially work with different kinds of underlying devices. And that's just what I mentioned here, right? I want this to be generic. And that's just both because it's not a nicer way to write code, but also I think it's kind of illustrative of, it's kind of getting deeper into the process and not only showing like the technological side, but also like going like a tiny bit deeper into like trying to make this a more well-rounded learning experience, if you will. All right, so we can go into the driver. I don't think I really changed anything in here since the last time we looked. Actually, I did, because this is the wrong file. So if you'll give me a moment, that is kind of the exploratory code I've been writing in the meantime. And, well, if we looked at that, we're not going to write anything interesting. So let's actually get the old code, which is here. Yeah, that's here. Let's actually bring it in as sddriver.old.ts for now. And then let's actually move sddriver.ts. Let's move that out to ljs/sddriver. Right, and hopefully in my other window I can actually still see that. I can. That looks good. So now we have the driver old. Let's rename it to driver. And this file should be pretty much as we left it for the most part. So yeah, we kind of got to this point last time. We were doing the initialization of the FAT32 system. And yeah, we kind of got to the point where we read the root directory. We kind of analyzed it in a hex editor. We kind of identified some stuff. And in the end, we pulled out all of these pieces of information, like the file name and the cluster and the size and all of that. We ended up reading the block that it was in. We converted the contents to ASCII, and then we printed it out, and we had the hello world file. So that's that. We can actually get rid of kind of everything till there, I would say. Let's press save. And the first thing we're going to do is to just refactor this SD card a little bit. So I'm going to write an interface, because an interface is going to be a good way for us to describe a block device in general, and you can then go and implement your block device in any way you want. It doesn't even need to be a class. It can just be an object that has some functions attached to it. But kind of the interface for what I call a block device, well, that's going to be, we're going to have read, and we need to read like from a certain address, basically. Let's call it block address. These names don't need to be the same, I think, in TypeScript. So we're going to read a block address, and we're going to return from that a promise of a buffer, like a node buffer. And a node buffer is just like some binary data. So that's that. And we already do this, right? In the SD card, we have a method called, let's take a look. We've got something called read block. Let's actually call it read block. Yeah, read block. And we call it SD read block, and we're just going to change that so that it matches this. And then, of course, we're also going to have write block. But for now, we'll just leave that out, because we're not going to be writing blocks today, although that is kind of the next logical step. And the reason we're not going to write blocks is because if we get into file writing, even though it's kind of covers all the same concepts we're going to look at today, it's quite a bit more in depth. But the concept should be there after this. So I'll say that all we need to implement for this interface is going to be read block for now. All right, so we can say that SD card implements the interface block device. At the moment, it doesn't implement the interface block device because it's called SD read block. Yeah, and actually let's call this LBA as well, because that's logical block address, and that's what the SD card also deals in, a logical block address. Right, so all I'm going to do here is I'm going to rename all of these things. So instead of them being SD send command, which is kind of redundant anyway, let's make it send command. SD await response will be just await response. SDRX, I guess we can call it RX. I might call it receive now. Yeah, instead. Init is fine. I guess we need an init method as well. So let's say we take init, and that's just going to be promise of void. So that should be this. That does that. And read block, if we change this now the read block, I believe we actually fulfill the interface now. So the SD card is now a block device, and in the FAT32, instead of taking an SD card, let's actually rename this to block device. And let's say that it doesn't have to be an SD card, but it has to be a block device. And then block device. And then that should also all be good. Like everything here is the same. Like FAT32 just takes a block device and we happen to be passing in an SD card, which is a valid block device. But that's it. Everything here should work the same. And I believe, yeah, I believe it's not like the code wouldn't work directly now. Wait, maybe it would. Oh no, I deleted some stuff here, so it's not going to work directly. But that's fine. We're now at the place where we can begin to understand where we're going from here. So if we go back to the to-do, generalize the device, we've done that. Look at the file allocation table. Yes, so that's going to be our first next step. Just so we are all on the same page, this is the layout of the SD card right now. So at the root of the SD card, we have a file called bootrom. I believe it just says hello world with an exclamation mark, just like last time. We have a directory called dir2. Inside that is a file called sectors. And sectors is, well, we'll look at it, but it's just a binary file that has a bunch of bytes in a certain order, and it's going to allow us to see the, what happens if it's not such a simple file. And then we have another directory called sum directory, sum_dir, and inside there is another doc, like another document. And I believe that that one is some text from the Node.js documentation. And it's quite a large file. So we've got this is the layout. We can use this as a reference. And yeah, so let's go and check the file allocation table out, because that's going to be how we proceed from here. So if we go back to Paul Stoffrigen's website, PJRC, and this article about FAT32 file systems, what we were getting into last time is that we got into this part, we realized like, oh, okay, here is a bunch of boot code that we're ignoring. Here is the place where the first partition starts. We got the information out of that partition, which gives us like enough information to know where to go and grab, the first bits of data that we need. And then, so that tells us like how to get to like a directory structure. And then we basically found this directory block, and the directory block has 32 entries, and the entries are basically formatted like this. So the first couple of bytes are a short file name. Then there's 1 byte which describes the attributes of that. So basically the attributes are things like basically telling us, is this a directory? Is this a file? Is this a special file? Should we say that this is read-only? Should we like show this in the file listing? Is it hidden? So just some kind of attributes there. Then there is some actual other data that goes on inside here, but it's not super relevant for our purposes. But we could take a look at it. And then there is a cluster high and a cluster low description here. And a cluster is, and we got into this last time, but if we go back to some of the variables that we extracted when we went through this, we ended up getting a bunch of information, like the number of reserved sectors, the number of sectors per FAT, the FAT begin LBA, so the logical block address where the FAT is found, or the first part of it is found. The cluster begin LBA, so that's the cluster number of the cluster begin LBA. So I believe that that is the FAT plus 2 times the number of sectors FAT. So that's basically telling us like where the next, well, we'll take a look at that in a second. The number of sectors per cluster. So all of these things right now, then they don't make too much sense, but these are going to make sense, and this one is going to become quite relevant. And the root directory first cluster. So the root directory first cluster, that is the place, like kind of with an address that we can't immediately use with the SD card, but it gives us a kind of address of where we can find those initial files, like where we can find this first directory. So we won't see this part yet, like, you know, what's inside the directory 2 and some directory, but we can get the first bit of information. Yeah, and we basically do that by reading out this information, and then we have to be able to convert a cluster to an LBA. So a cluster is like kind of how the FAT32 file system treats data and how it kind of spreads things out. And an LBA is the logical block address that is a 512 byte block that the SD card is concerned with. And so we need a way to kind of convert between those. And this is kind of the formula that we use for that. So let's actually pull that out to a function or to a method, which will be called cluster to LBA, because we're going to need to use that a couple of times. So we'll take a cluster number, and from here we can actually just return this. And instead of returning the root directory first cluster, which is a specific cluster, we're going to return the cluster the user passed in. So this now will give us a place that we can directly go and ask the SD card for information from. And this is something here to note, is that we end up taking this cluster. It's kind of offset by the beginning of the cluster begin LBA. So this is actually an LBA already. And we can get to an LBA by taking a cluster and multiplying it by the number of sectors in a cluster. And a sector is actually, in this case, it's the same as a block, right? So a sector is just a 512 byte piece of data. So basically a cluster is however many sectors we have. A cluster is however many sectors we have, however many blocks make up a certain piece of data that the FAT32 file system is concerned with. And I believe, and I would need to run this. Actually, let's do that. Let's just run this, put a debugger down, and we can look at what some of these values come out to be. So I'm going to plug in the device here, and I haven't tested this today, so I do hope it works correctly. TS node SD driver. So I'm going to run that. And I'm looking, there are some lights blinking, there's some data coming through here on the screen, so that's good. And I've just realized that I didn't run this with the debugger, so we're not going to be able to inspect those variables, but let me just run it again with the debugger. I see that the device is unavailable because we're actually we're attached to the device right there, so that's not going to work. So we close that. I can see that the device is blinking, and yeah, we're at this point. So what we can see is that the number of sectors per FAT is like this number, and the number of sectors per cluster is 8. So there are 8 sectors in a cluster, and we know that a sector is 512 bytes, right? It's the same size as a block. So 512 multiplied by 8 gives us 4,096 bytes per cluster. So a cluster is a 4 kilobyte section. So we're dealing with stuff in 4 kilobyte chunks, basically. All right. This is probably all a bit abstract at the moment. I do understand that, but hopefully as we start reading information out from the system and grabbing stuff, it will become a little bit clearer. All right, so we're going to need to keep track of some things, right? We're going to want to keep track of like which directory we're currently looking at. So we're going to start out looking at the root directory. We're always going to start out looking at the root directory. So let's keep something called a current directory. And that's going to be, well, how do we do this? I think, so this root directory block, this is a 512 byte buffer, and this actually represents right now the root directory. But there's not that much use in us like kind of keeping track of this as like our current directory, because it's kind of really raw information. We kind of need to extract the information. So let's actually write now a method, and this is where I shouldn't have deleted that code that I wrote here in the beginning, because we kind of already did most of that. So since we wrote that in the last episode, I will actually copy it from this other place that I have it. And actually, let's just write it again, so it's not too much. So we're gonna take a block and extract directory information out of it. So let's do that. Get directory data. So we're gonna have a block, which is just a node buffer, and we're gonna assume that the data inside that buffer is a directory. So where do we get that information? Well, we did this last time already. We know that that there are these sections within here which are basically telling us the file name, the attribute, the cluster high, cluster low, and the size. These are the pieces of information we're going to extract from each entry, and we're going to kind of present them on the screen. And yeah, so let's actually do that. And well, of course, there aren't that many entries in here, right? There aren't 32 files for sure, right? We know that there are going to be 3 entries inside here. So when we encounter an entry that begins with 0, then we know that like we've reached the end of the entries. There are some other special values that we'll use as well. But let's basically just make a loop here. We're going to need a type that holds like directory information. So let's have export type directory entry. And a directory entry, well, it has the short name, which is a string. It's going to have, what else do we have here? We have the attributes, we have the cluster high, cluster low. Well, that we'll just make that cluster and size. So attributes, just call it attribute, which is a number, and cluster, which is like our address basically. We could already convert that to an LBA, but I think we'll keep it as a cluster for now because it's easy for us to translate that in the moment we need it. And we're going to see that the rest of the system deals with clusters, so we're going to want to be able to cross-reference cluster numbers together rather than LBAs. And obviously we could actually go back to LBA, right? The formula that we have, we could just rearrange it and go back to LBA from cluster, but there's not much use in doing that for now. So cluster, and what was the last one? File size. And keep in mind, some of this is also not going to be like super relevant. Like if it's a file, obviously having a file size is going to be meaningful. But if we're dealing with a directory, like a file size won't matter, so we'll just make it a like a 0 in that case, or some other number. It won't be kind of really defined. So from this method, we can actually now say that we return an array of directory entries, and we don't need to make this a promise because we already have the block. So we don't need to like read the block from somewhere, and that takes asynchronous time. We just have the data, so we're just going to process the data in real time. All right. So we're going to basically be getting some entries as we go along. These entries are going to be an array of directory entries, and eventually we're going to return them back to the user. So how do we get them? Well, we're going to basically, we're going to loop through each of these 32-byte sections. Because, again, just to really drive it home, we have this 32-byte directory structure. So this whole line is 32 bytes. So we just need to, like, starting at the top, like read this whole line, extract the information, and then add 32 bytes and read the next line, and do that as long as we have information left to deal with. So we'll start at 0, and while offset is less than 512, which is our block size, we will add 32 to the offset each time. Pretty straightforward. Okay, so now we can start getting the information out. So the short name. To get the short name, we need to read 11 bytes here from this short file name. So we can do that. Basically, we would say block dot. Yeah, we can actually do it like this: block dot slice. So we'll have another buffer that comes from this, and there's a reason that I'm not converting it directly to a string now, and we'll look at that in a second. But so we're going to start at let's do it this way. Let's grab what we'll call byte 0, so the very first byte of the short file name, and we get that just by like looking at the block at that offset. And as I mentioned before, right, if byte 0, hey team LOR, if byte 0 is 0, then that means that like we've kind of reached the end of the directory. There are no files to be found here. There are no entries, so we're done basically. So at that point we can just break out of the loop. Let's just put that on one line. And then obviously if it's not 0, well then surely we have a file name. But there's actually a little caveat here. And so these are the 4 things that this could be. So the normal record with a short file name, well, that's when the attribute is normal. So if the attribute is normal, then we just have a normal file. But then there's something called a long file name text. So this is one of the things where it's not exactly sort of this nice, beautiful 32-byte structure that always means the same thing. Obviously, you only have 11 bytes for the file name. That's not enough for a lot of file names, right? That includes the extension. So if you have a file or a directory name that is longer than 11 bytes, the way this is done in FAT32 is that, well, they'll make a bunch of dummy entries in this table, and those entries will just contain information about that name. And so it will start at the end of the name, and you'll be able to pull out some number of bytes from that. You can't actually pull out 32 bytes, but you can pull out a certain number of bytes for that describe that long name. And from that very first record, you know how long the name is going to be, because you know how many bytes per 32-byte row you can extract, and you know kind of when the name ends, because the name will end with a repetition of a bunch of bytes. I think it's hex 20, which is a space, right? If the file name ends in a bunch of spaces, that means it's the end of the file name. So you can actually work out in that way exactly how many how many bytes you need to store. And obviously it also includes a sequence number, so it says like how many of these 32-byte rows are gonna be coming in order to finish this this file name. We're not going to do any of this long file name stuff today. I just want to put it out there that it exists. There's some interesting comments going on. Stuff about hacking into Roblox. It's not really my bag there. Alright, so we're going to ignore these long file name entries, and this is quite easy for us to do because the attribute byte, which is here, if we read that byte first, well, we've read byte 0, so we know if something is an end of directory. We also can then just read the attribute byte, and then if the attribute byte has the first four bits are all set to a 1. In other words, if this is this whole byte is F, in that case, that's a long file name record. So we can ignore anything there that happens to come along. Also notice that there is this unused thing, so the first byte is E5, so we can also ignore those records. So let's actually go back and implement all of these things that we ignore. So we ignore 0, and let's give these things names because I don't like just having magic numbers everywhere. So const FAT32 directory entry. If the directory entry, what am I looking for here? End of directory. That's going to be 0. These aren't the best names, but they'll work for now. Unused entry. That was E5, and well, those will work for now. So if it's FAT32 end of directory, then we break. If it's FAT32 directory entry unused entry, then we also break. We could also put these in like a thing. What happens if a directory contains greater than 32 files or subdirectories? Yeah, that's actually a really good question. That's kind of where this where a lot of this is going to hinge, because it's exactly the same for what happens if a file contains more than 512 bytes. That's kind of the question that you're asking, right? Because there are 32 entries, and in total, if you multiply that out, right, that you get 512 bytes. And so what happens if you have any time something that takes up more than 512 bytes? And that's where these sectors come in, right? Sectors per cluster. We're actually dealing with clusters right now. So even though we've read a block, we're in a cluster. And a cluster is a bunch of sequential blocks. And it's actually 8 sequential blocks in a row. So what's going to happen is that for a directory or a file, we're going to have 8 sequential blocks that we could read. And so basically we've got this LBA, right? For the root directory block, we have the LBA. And if we want to get the next, like the next sector, we just add 1 to the LBA and we read that block. So that's how that works. And that's going to work for files as well. And then obviously the the chicken and egg question that comes from that is, well, what happens when you have a file or a directory structure that needs more than 4096 bytes, right? Because that can happen. And that's where we'll get into the file allocation table. Yeah, which I was saying that we were going to look at straight away, but it's better that we get this directory information out first because we're going to need this to do everything anyway. So we will get to it. So someone asks, do you have near field communication? I don't have any hardware like in my immediate surroundings that has NFC, but Yeah, there are NFC modules out there, and I'm pretty sure they're going to either speak SPI or I2C or something like that. So it's perfectly possible that I could get a hold of an NFC module, and then we could write some drivers for that as well. What I do have, and that I would like to cover in the future, well, I've got a bunch of hardware here that I would love to cover in the future, and time is limited, so we'll see. But I've got these like NRF Nordic Semiconductor kind of SPI wireless communication modules, and I think it would be fun to write some drivers for these, because these are pretty like interesting wireless devices. Like I can build something on an Arduino or like on some microcontroller that's got like doing some known communication, and we can build the other side of it in Node.js, and we can just do wireless communication. So that's something I might want to do in the future. I don't have any NFC, but maybe I'll look into it. All right, so what we need to do is we need to read the attribute, and the attribute, we need it anyway, so it's fine to read it. We can read things out of order, right? There's nothing forcing us to read bytes in order. So we can first read the attribute, and then I think I actually already made some constants for these. So the attribute offset. So we already have all of these offsets known. So if we have our current offset and we add to that the FAT32 directory, and what's it going to be? Directory entry size, attribute offset. Yeah, so if we just add the offset, then we'll read the attribute. It's just 1 byte as well. And then we can actually check if the attribute is equal to F0. Sorry, 0F, because it's the least significant bits. If those bits are all 1, then we're ignoring those as well. So let's actually make an entry for that as well. So it's going to be directory. It's not really directory at this point. So directory entry unused, end of directory, and this one's going to be like directory entry long name. Let's just do it like that. 0F. So cool. If it's a long name, we're also going to ignore it. And now from this point on, everything's easy, because sorry, I'm looking at some of the comments here. I see that Furcon has asked the question, I'm trying to use an old gamepad for Windows XP, but I have Windows 10, how can I use it? Yeah, I don't know specifically. If it's USB, which maybe it is, right? If it's a USB device, there's probably drivers out there for it, which would still work. Probably still work for Windows 10, I think you said. Although I'm not sure. It depends on if they're like proprietary drivers. If not, you could write your own USB driver for it, which would be an interesting experience. If you're talking about like an old gamepad that's like, you said it's for Windows XP, so it probably is going to be USB, but you can actually take old gamepads like Super Nintendo controllers and NES controllers, and you can actually build a little bit of hardware with an Arduino that can turn that into a USB gamepad as well. But yeah. You need to do some Googling for the drivers for that. I'm not sure. And if they're not standard drivers, like I don't think gamepad, like the gamepad standard USB driver existed at that point, so it probably won't work. PC can't see USB device. Yeah, so you're missing a driver for it basically. It's a little bit out of scope to go into it on here, so I'm afraid I can't really help with that. So we're going to slice from offset to offset plus 11, because that's the length of the file name. So once we have that file name, Actually, what we can do is now we know it's a file name, and we don't have to worry about, at this point, we don't have to worry about that first byte being some sort of indicator, so we know it's a string, so we can say that we've got ASCII string, and we start at offset, and we end at offset plus 11. So that should give us the name. And the then we get the attribute. We already have it, so we get the cluster high. And I realized we did this in the last thing, so I'll race through it. That's going to be block dot, and it's a 16-bit thing, so we're going to read a uint16 little endian, and we're going to read that offset plus FAT32 directory entry first high offset. Then we're going to get the low offset. Then we are going to just get the cluster number by combining those two things together. So we're going to take the low, which doesn't need to go anywhere, and we're going to OR it with the cluster high and shift that up by 16 bits because it takes up 16 bits. And then this gives us a 32-bit number for the cluster. And then finally, we just need the file size. And I believe the file size was the 32-bit integer. And that's going to be the file size. Great, so that gives us all the things we need for an entry. So we can say entries.push, and we're going to push in an entry that contains the attribute, the cluster, the file size, and the short name. And at that point, we should be done with the thing. So let's actually do this. Let's entries is going to be this dot get directory data. Let's call it get directory entries. And let's pass in the root directory block to that. And then let's just like console log the directory entries out. So I'm just going to run this. Hopefully this should work. And we got okay, so we got an empty thing. So I guess I probably got this wrong, right? Yeah. So there's a question here which is 32 bits file size means we can't store more than 4 GB. It's not really a question, indeed, but that's true, yeah. With FAT32 you can't store more than 4 GB files. I think that was a limitation with it, right? Maybe there are ways to get around that, right? You can also set specific kinds of, like, you can put little flags in, but I think it actually was a limitation. We're still getting 0 entries out of this, and if I look here at the bytes that make up that directory entry, directory block. See E5, so that first thing is unused, a bunch of stuff. E5. Let's dump that out and kind of just look at it, because I have a feeling I'm doing something wrong here. So there are a lot of questions at the moment in the chat which are about hacking, and that's my fault because I put the word hacking in the title, but this is not hacking in the computer security sense. This is like hacking like we're getting into like low-level code and we're like hacking at file systems. So we're not doing this for information security purposes, although there are some implications here if you're like an information security person or a forensics person and you're looking to recover data from like drives that you think someone has deleted the files from. Actually, the way that file deletion works in FAT32 can mean that some of the data is left over, and that's one of the things that we might see at some moment. Let's just call this directory.bin, and we'll just dump out the root directory block because, yeah, I'm have a feeling I'm missing something here, because we definitely should get some entries out of this. Yeah, like they can't all be like that. All right, so let's take a look at that in hex editor. So we've got bewitched here, so we can do directory.bin, and yeah, so here I can actually see my things, right? We've got bootbrom, we've got some directory, we've got directory 2. So we've got a bunch of stuff in here, and I see that some things begin with E5, right? So each record is taking up 2 of these rows. So that's 1 row. We ignore it because it's E5. We ignore this one because it's E5. We ignore this one because it's E5. This one is 42. So that looks like it should be good. And if we look at the this byte, I know this just because I know the layout of this now, right? And you can see where the bytes are in the column structure. This byte is the attribute byte, and it says this is just a regular file. So I can see that this one should return us something. So something else is going on here. Like the data is good. So let's see what's going on. Let's drop a breakpoint in here. Let's drop it here. And it takes a little bit. Like, this is not a fast process. Like the talking to the SD card in this way. Oh, that actually didn't work. Huh. Am I just like having a brain meltdown on for loops here? Like, while this is like offset is 0, while offset is less than 512, offset plus 32. All right, let's run that again because we didn't even hit the breakpoint. Yes, okay, so I don't know what's wrong with me. All right, so the first one, yeah, the first one we know, and let's just get the thing back open here, right? Because then we can compare it at the same time. This first entry, we know we're going to skip it, right? Because it's this directory entry unused. So we're going to get to that, and then we're going to break. Oh, we shouldn't break. That's the problem. Yeah. That's a nice, simple bug. Instead of breaking, we should be continuing. Right? We want to go back to the top of the loop. We want to loop again. We don't want to stop looping. Continue, not break. Yes. So someone got there a minute before. Thanks, Axel. All right. At least now, then, we don't need to write this file out anymore. And we should be able to see the directory entries. I'm going to get rid of some of this noisy stuff that's going on here with these outputs at some moment, but here we go. Yeah, we got the 3 entries. So we got bootrom. Its attribute is 32. In hex that's 20, and that just has the like file not written to backup or something. Like that just indicates it's a file. Then we have some directory, and you can see that has 16, and then that's in hex that's 10, and that indicates that this is a directory. So we know that both these things are directories, and we know that this thing is a file. So to read this file, like we get the cluster number, and we turn that cluster number into an LBA, and then we go and read the file. And to go and get the next directory entry, right? So we'll actually do this, because why not? Like that's at cluster number 5. So in some directory there's a cluster number 5, and like we'll turn that into an LBA, we'll read it, and that's also a directory, and so we can use that to kind of move through directories now. And then what we'll do is we'll store our current directory. We'll actually just store this piece of information because this is all we really need, right? This is the condensed version. All right. So in order to do that, let's give ourselves a current directory. The current directory will be a, what are we going to call it? It's an array of directory entries. And at the beginning, it's just going to be empty. We don't have anything in there. And what we also need is this idea of like which sector are we looking at. I guess we actually need to be able to read multiple sectors. One of the things we could do, Oh wait, so if we get to the end of the directory, then we actually can break. But what we can say is, let's do this. And this is going to be outside, I guess. Like, we want to know if we reach the end of the... Like, did we reach the end of the directory? Because if we didn't reach the end of the directory, we kind of need to like load up the next block and read from it. So what we might want to do is, instead of, to get a directory entry, instead of like parsing a block, maybe what we'll do is we'll pass an LBA and we'll do the block reading here ourselves. So let's take an LBA in, which is a number, and then we can actually get the, yeah, we can read the block. So we're gonna, sorry, I'm doing a bunch of stuff at the same time here. So we're gonna get our block. So let block equals await this dot SD, or not SD because it's not SD anymore. It's a block device. Read block, and we're gonna pass an LBA in here. And we shouldn't pass an LBA. We should pass a cluster number because we're gonna need to use our formula and figure stuff out from here. Do we do it like this? Yeah, let's do it like this. So it's going to be this dot cluster to LBA. This is our cluster number. So then we are, and this is saying this isn't async. All right, so then we're going to say that like our current sector, and our current sector is going to be 0. And then what we can do is something like this. We can have a double nested loop, like a double loop, and we'll say for let, I guess we can do that outside of here. We can say let cluster, sorry, sector. Call it sector offset. Yep. Sector offset equals 0, while sector offset is less than this dot, what is it, sectors per cluster, sector offset plus plus. And then what we can actually do is read the block inside there, and then just add the sector offset. So I hope this is clear. We take the cluster number, we convert it to an LBA, which is also just a sector, and then we add a sector offset, because there are 8 sectors per cluster. So we start at the beginning, we're going to read that sector, and then if we don't have, like, if we need to keep going, we can actually read the next sector and then get more files. So I hope that's making some sense now. So we are going to dump that inside here. And then, so then we're reading that block and entering this loop. And so what we can see is if we get to the end of the directory, we're kind of done in general. So let's make a variable outside called let done. And let's say that by default is obviously false. And here we'll say done is true. And we will break, or actually break, from this loop. And then that's going to spit us out down here, and we can say if we're done, then we'll want to break out of this loop as well, because we have all the entries. So in this case, it's not going to make a difference, because like we know that there's only one sector that has data, but this now should work for in general. Apparently we're not returning. Oh, so this needs to be a promise of that. Yeah. So I think we don't even need this annotation anymore because it's clear. So we can actually just get it from there. And what we can say is that current directory, so we'll do it like this. This dot current directory equals this dot get directory entries, and the cluster number is this dot first root directory first cluster. Great. And yeah, all of that should work the same. Nothing should have changed. Sorry if you can hear the rain coming down on the thing. Yeah, so that works the same. Yeah, there's a big storm going on in Europe at the moment, and yesterday, like, trees were falling down and everything, and yeah, it was it was not a good day to be on the road. But yeah, today it's just raining, but hopefully the sound is not too bad. Can you hack PlayStation? Where can you get free games? Don't know. Sorry. You can hack a PlayStation for sure. Like, I know you can do that. But I don't know where you get free games for it. You have to do some Google searching. I think you need offset times cluster size when reading blocks. Offset times cluster size. So here, when we're reading blocks, so sector. No, but the reason we don't need to do that, the reason that we don't need to multiply by cluster size is because cluster size is 4K, right? And this gives us the first sector from this cluster. Like, the cluster is the 4K thing. This gives us the very first sector, and then we're looping through and adding the next sector on, and only up until sectors per cluster. So we'll only read 8 sectors from this cluster, which means we'll read 4 kilobytes maximum. So that's how this should work. And of course, this isn't the end of the story, because if this directory has more information than that, then we actually need to go to the next thing, which is going to be the file allocation table. And I think now is a good time to actually already go and check that out, because we're already at the point where if we wanted to write a complete version of this, we would need that. So let's zip back to the browser. So files and the file allocation table. The file allocation table is actually a really simple concept. It's not hard at all. But I was confused by it when I first read, like, the Wikipedia article. So there is this great article here called The Design of the FAT File System. And it tells us, for instance, that this is the layout of a FAT file system. Like, in the beginning, you have a bunch of what they're called reserved sectors. So, like, this stuff not used for files and that kind of stuff. And what it has is the boot sector. It has a file system information sector. And it has a bunch of reserved sectors, and we've abstracted that away because we read that information from the boot sector, and we just skipped over it. So we then get to the FAT region, which tells us, like, how many, like, it gives us our file allocation tables, which we're going to take a look at. And then we have the data region, and the data region is, like, that's where all the files are in the end, and also where, like, directory entries are. So this is just everything else on the disk, and it's organized by clusters, and we will go and read blocks, and blocks are sectors, and sectors are clusters, and blah blah blah. So that's how that works. So the FAT is basically a let's see, there is a diagram in here somewhere of, like, what the FAT is, and it's this one. And these ones are for FAT12 and FAT16, and since they're not the file system we're dealing with, let's just skip over them. And so this is what a file allocation table looks like. And this is, like, a really confusing looking document, or a really confusing looking table, until you understand what it is telling us. So we need to look at 32 byte, like, each entry in this table is 32 bytes. So that's something to keep in mind. So the cluster 0, that's that's what we call here the first entry. It has this special number, which is like, kind of like a magic number for the file allocation table. And then the second one is also unused, so it doesn't actually refer to anything. And it is so it's little endian, right? So this is like it actually is 0f, ff, ff, ff. But this value can potentially be anything from FF, sorry, 0F, FF, FF, F8 up until FF. So in that region, that tells us like that this is a special value. And this special value, and in these first two entries don't mean anything, but the second entry actually uses the special value. That special value says that there, after you read the data at this cluster, there is no next cluster which has information. So this one is for cluster, and just, I'm a bit all over the place here, but I want to go back to the code and just look at something that we saw in the previous one already. But you'll notice that in the cluster, when we're converting a cluster to an LBA, we get the sector or the LBA where this begins. And then we add to that some offset. And this offset is the cluster number minus 2 times the sectors per cluster. And the minus 2 is where this comes from in the file allocation table. Those first two entries, they don't mean anything. So this is actually the very first entry. They call it the one cluster. Like, I think it doesn't matter. It doesn't begin at 0 or it begins at 1. It doesn't matter. But I'm thinking of things 0 indexed all the time. But what this is telling us is that if there was something that was at cluster number 1, there wouldn't be any data following it. So then when we go to cluster number 2, like we can go and read the data there, and if we we have to go and check, is there more data to come after this? And the way we know that, well, one, the directory entry tells us the size of a file, so we know if a file size is like exceeding that. Now I say that, I do actually wonder if a directory entry has a size that corresponds to the number of clusters it takes up on disk. That could be the case. That would be a really useful piece of information to know. So what we'll see is that if we were here, this is sector number 2, like we would read the data there, we know that there's more data, so we come here to figure out where the next piece of data is going to be. And the next piece of data is going to be sorry, I'm getting myself completely confused here because of this minus 2 offset. This is still the first entry. This is still the second entry. This is number 3. No, that can't be right. This must be number 1. This is number 2. And then it's telling us that 1, 2, the next piece of data is telling us should be at the 4th entry. And the 4th entry in this table should be... no, I'm getting myself confused, right? This is the 4th, so 0, 1, 2, 3, 4. Yeah, and then this one's telling us it to point to the next one, which is 5, which is this one. This points to 6, which is this one. And then this one points to that, and then eventually we get the end of marker. I hope that some of that is clear. I'm going to try and explain that again because I got myself all confused about it. So this is what is considered to be cluster number 1, but it doesn't have a, or it's cluster number 0, right? But it doesn't have anything there. Cluster number 1, cluster number 2, and then this is cluster number 3, and then that is telling us that when we read all the data, if we come here and we index by cluster number 3, so we work find ourselves the 0, 1, 2, 3, this entry tells us what the next cluster is, like where is the next cluster that we find things. And you see that it has the number 4 here. And remember, this is little endian, so the smallest part of the number comes first in little endian. So it's actually 0400, sorry, it's 00000004. So then we would go and read that data by using our cluster to LBA formula. Then we can actually come back to the FAT and we can see where the next piece of data is. And we do this continuously until we reach this marker. And if we reach this marker, which is 0f, ff, 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 it could be different values. It could actually include some 8s in there. Then we know that we don't need to read any more data. So I hope that's clear. That is how it works. That's how we index into the FAT. So just catching up with the comments here. Are you building an operating system using JavaScript? No, I'm not. I'm just at the moment building a connection to an SD card and reading data directly from the SD card. There's another question. So cluster 0 has no data. Yeah, so cluster 0, it doesn't have anything. It's just this is like a start of file allocation table marker. And then cluster 1 also doesn't have any data. That one's also always set to this. And then the beginning is cluster number 2. And that is the reason that we have this offset, is because there would be no reason to store like 8 kilobytes of useless data. So like they just say that clusters actually begin at 2, and then we do this offset thing so that we don't waste any data, like when we're using the formula to find data later in the drive, basically. Just joined the stream. What exactly does file system hacking mean? Yeah, it's a bit tricky to get into now. You can watch the previous stream. That also goes into what it means. Basically, it means that we're talking to the file system at the very lowest levels, and we're building the layer to actually read, write, delete files from scratch, from the ground up. So that's what that means. Okay, so now we kind of know something about the LBA. Sorry, not the LBA. The FAT. That's actually like let's actually read some files, because I don't want to spend any more time on this directory entry thing, because it's not going to like give us any more information. Like we don't have any directories that have more information or that span multiple 4 kilobyte clusters. So let's instead find one of the files on here, and we know, for instance, that like there's another directory here, like some directory, and inside that there's some information. So let's read that. So let's do this. We first set current directory to this, and then let's set it again to this dot get directory entries, and we're gonna find the a directory entry in here that starts with some directory. So we can do that by like finding the item in here. So this is going to be an entry, and we just want to return entry dot short name dot starts with and some directory. So that's going to tell us what is in this directory. So what's going on here? Returns the value. What doesn't it like here? Oh yeah, we need to return the cluster number. So when we find that, then we need to say cluster. Yeah, this is a bit bad code, because like you know, this could fail. Like we might not find this operation, but we're treating it as if we do. So this isn't really the best way. This is not solid, but right now we're just experimenting. So let's run the driver again, and we should see another directory entry after this. We don't see it because I don't log it. And what we're going to do now is we're going to find one of the files in there, and we're going to like, yeah. So what we get here, this is interesting. When you go into some directories, what you'll find is that they have a dot and a dot dot, right? So that's the current directory. So we store an entry that tells us where we are right now, so cluster number 5, and we store an entry which tells us how to get back to the parent directory, right? So this is what the ... yeah, so reshout, the reason it's bad code is because if there didn't happen to be a directory or a file or a short name that started with some directory, then this wouldn't work. It would actually fail. So that's why it's bad code. The cursor's strangely familiar. Are you on GNOME desktop environment? No, I'm using... oh, I don't remember what the name of this desktop is. Well, the desktop environment is Cinnamon, I think. And my window manager is SD something something. Yeah, I don't remember. I switched to it recently. But no, it's not GNOME. I haven't used GNOME in years. Alright. So I actually want to look in the other directory. Like, what was the other one called? What did it have in it? Directory 2. So, dir2. Let's do that one instead. Alright, yes, and there was this file in there called sectors. So let's use that, because the file size is 1024. Actually, this is also a bad file to use, because it doesn't cross a cluster boundary. It only crosses a sector boundary. No, it's not XFCE. It's a lightweight desktop manager as well, though. Window manager. So yeah, did we have something in that? Not some directory. So that has sectors. This has this another. Yeah, so this is the one. This is the one that I want, because the file size here is like 27 kilobytes, which is like quite a large file size. So this is gonna include going over and looking at the FAT and being able to track some stuff down there. So let's just make a note. The cluster is 20. Let's we're gonna keep track of the FAT, which is also going to be, and the FAT's a buffer. It actually makes sense for us to keep that as a buffer. We don't need to process it. We could process it, but I don't think it's worth doing. And let's also keep track of the FAT sector offset, which will start at 0. So when we load this up, one of the things we're going to want to do is to get the FAT. So we can do that with await this.blockDevice.read block. And the LBA is going to be this dot, and we actually have the FAT begin LBA. We don't even need to compute that ourselves. So the FAT begin LBA plus this dot FAT. We don't need to do the FAT sector offset because it's going to start at 0. Yeah, so like the quickest of quick recaps, basically we are writing a driver for an SD card. So here you can see, if the autofocus works nicely, which is probably not because I can't see what I'm doing. This is waving around. It's not going to focus. Anyway, we've got an SD card here. It's attached by a bunch of wires into this device. This device is called the Bus Pirate. It's wired up, talks over USB, and it allows us to talk multiple protocols. And we are writing like the very low-level code to talk the protocols and talk to the SD card and eventually get to the file system on board. We're writing the code for that in TypeScript because we can. And so yeah, so basically that's what we're doing right now. So we're talking to the file system at the lowest possible level. Alright, so we get the FAT, and now we have the FAT. Let's actually just dump it out to the file system so we can take a look at it. So fs.write_file fat.bin this.fat, and then let's run this again so we get that. Okay, so we should have the FAT now. Alright, so this is our file allocation table, and you'll notice that it looks pretty similar to what we saw already in this diagram, although of course we don't have the fancy colors that the Wikipedia one has, which they're not very nice colors anyway, but they're certainly bright. Alright, so we see that it starts with this F8, FF, FF0F marker. We can see that the next entry is also the same. And what you'll notice here is that on my system, the kind of no more clusters in this chain marker is FF0, FF, FF, F8. So that's the marker that's used on my system. So we actually, because I want this to work relatively, but like with multiple different SD cards and not just like this specific one or however this one was formatted, I'm gonna say like that what we might do is to, yeah, we'll look at a range. We'll basically figure out like, is it like from this to like from this number to this number basically. Okay, so that file that we were looking at, apparently I can't scroll back in here. That's okay. Yeah, that's not super helpful. So cluster number 5, so 0, 1, 2, 3, 4, 5, we can see that that directory doesn't have anything following it. All of these 0 entries mean that this is an empty cluster. There's nothing at this cluster. So if there's a 0 there, it means that it's an empty cluster. That's quite a useful thing to know. And then one of the first places that we'll notice is that there is a different number is here. So presumably, if we arrive at whatever this is, we need to read 15. I think that'll end up being this one. Then we read 16, 17 onwards. So I think this is actually the file that we're looking at. This is the file that we're looking for. But we're going to do that obviously through our system. So let's get rid of that, and let's get rid of that. And at this point, when we have the FAT and we have the current directory, we kind of are done with initialization. So let's do everything else from here. So let's say we want to find this file. So we need to move into that directory, and we need to move into that directory and like find the file that we're interested in. So in order to get into that directory, we're going to say so some directory, and well, let's do this the manual way first, and then we'll see how we would get this in the like what a better way of doing this would be. So now I have the directory entries, so the current directory. What we want to do is like find a file in here from exactly the same thing we did before. And we want to find, so it's going to be the return entry dot short name starts with, and it was like some directory. So that's going to give us a directory entry, and if we don't have that, then let's just like throw an error. Do it like that for now, and then once we have it, we can say to the FAT32 file system to go and like read that. So it's going to be like get directory entries for some directory dot cluster. What we should notice here, right, is that like what would actually be a nice API for this would be something like this. We would have like FAT32 dot open directory, and we could do something like this, right? This would be a nice way of like setting this API up, and you could see that we could build that out of these pieces, right? So we could like split this string, and we could say, okay, this is the first directory, so what we need to do is we need to find an entry in the root, then we need to see if we got that entry, see if it is a directory, blah blah blah, and if it is, okay, then we're going to get those directory entries, and then we're going to find like the next thing. So maybe we have another directory there. Okay, let's now find this directory in that list in the same way. So this is an API that we could basically figure out. I'm not going to do it for now because it's kind of like just a sort of nice to have, and we can deal with the low level components for now. In the if statement, you might need a exclamation mark right in front of some directory. We want to find an entry in this thing whose short name starts with some directory. Oh yeah, you're right. Yeah, sorry about that. Yeah, you're completely right. Right, so then we're going to get the entries. So this is going to be the some directory entries. And what we want to get from those, this actually does return that, right? Yeah. Yeah. We're going to get those directory entries, and then we want to find the file. And I don't remember what the name of that file was anymore, so let's just log them out. Actually, I know what the names of the files are because I have them here. So in some directory, there's something called another doc. So let's try and find another doc, and that's going to be just doing the same thing on these, like finding, and we're going to find the one that starts with another. It's going to be something like that. We don't need to find the exact thing right now. So just so we can like freak out on like all the possible things that don't work. So we're going to get that document, and then what we can do is we can start to read this document. And how we would do that is like, well, the first part is just like we convert the cluster to an LBA and we go and read that LBA. But we actually know the file size of this thing, so we know like we know what's going on with this file. So if I just ts node sd driver, if I run this and we get all this information off the card, yeah, like we know that this is a 27 kilobyte or so file. It starts at cluster 20. That's 20 in decimal. It has attribute 32. So we can look at that. So what I want to do actually, and we'll just keep a note. Let's just like keep this around for now, because I'm not going to build all these nice APIs for like open file, which takes a path and that kind of stuff. So we're going to have that. And we've got that information, so we're kind of done with this now. We'll just get rid of it. Let's write a read file function, or a method. So when we read a file, we're going to take a directory entry. So let's just take an entry, because that directory entry tells us everything we need to know. It tells us like the attribute, it tells us the cluster, the file size, the name if we care about that, but we don't. The only things we really care about are the cluster and the file size, because that's going to tell us like how many bytes do we need to read and where do we start. All right, so first things first. I'm out of water, so hopefully my voice doesn't completely cave in. All right, first things first. We want to check if this is actually a file, right? That it's not a directory or something like that, because if it's a directory, it doesn't really make any sense. And if it's any of those other things, it doesn't make sense. So let's go back to Paul's website. Let's just look at this table again. And we know that something is a file if it has bit 5 set, right? And bit 5 means that it's going to be, what is that? 20, hex 20. So let's just make a couple of constants up here. Yeah. Oh, I actually have a constant for this, which is 32, so I should have used that. So let's call it directory entry, or wait, let's do it like entry. These names are getting really long. Entry attribute. And this one is going to be, let's just call it file. That's 20. Directory. That's 10. Are there any other ones we care about here? I don't think so. I think we really only care about files and directories at the moment. We're going to ignore like read-only and hidden and stuff. We're not going to respect those for now. Yeah, that's pretty much all we care about. So we can check the attribute. So when we get the entry, the first thing we can do is say entry.attribute. If it's not equal to FAT32 directory entry attribute file, throw new error, cannot open non-file, and then we'll just print out like what the attribute is. So I think we have this 2hex function. We don't have the 2hex function. Up to L with zeros, right? All right, so that's that's our safety net, right? Once we have that, then super easy. Now, Axel asked the questions. Are you planning on making your own file system? At the moment, no, right? I'm just interacting with an existing file system. But what I do need to know is like, how do I read a file from the file system? How do I write a file to the file system? Because for instance, if we make a new file, we're going to have to find some empty cluster. We're going to have to write our data there. We're going to have to update the directory entry. We're going to have to update the file allocation table. So we need to know how to do all of these kind of operations. But I'm not doing it from scratch. So I'm not just starting with an empty system and then writing all of that stuff. Although we could do that, right? Because the information is there. But I'm not doing that right now. All right, so we're going to read this file. We need to figure out how many well, there's a simple way, like mechanical way we could do this, right? But we know, for instance, that we have 20, like this number is like how many bytes we have. So the number of clusters that this takes up is going to be taking this number and dividing it by 4096, right? 4 kilobytes, because 4 kilobytes is the number of like the amount we can have per cluster. So if we divide that up, we get 6.61. So we know that we span 7 clusters, right? Because you can't have 6.61 clusters. You just have a full cluster. So there are 7 clusters. And then if we further divide that by 8, right? Because actually we want to know, well, if we just do 512, this is how many individual blocks there are involved. There are 53 blocks that we have to read. Yeah, 53 blocks that we're going to have to read. So it's going to be a pretty slow operation over this connection. That's mostly down to the bus pirate. It has to do a bunch of buffering in between. But yeah, this is going to end up being kind of slow. But in the end, we're going to be able to see the full file. So I'm all right with that. So I think the easiest way to do that is going to be is to have something like this, right? The number of clusters in this file is the we have to round up. We did the rounding in our heads before, but we'll do real rounding now. So entry dot file size divided by, I'm just going to hard code this for now, but 496, 4K. Or actually, let's do it like this: 512 times by this sectors per cluster. That's at least a little bit cleaner. All right, so that's the number of clusters that we have involved, and let's have a sector offset because we're going to need to like span over multiple sectors. So there are just a lot of different ways that we could do this, like how to keep track of how many bytes that we're reading and when we're going over sectors. But in the end, we're going to need to know, like, okay, we're moving over this this sector or this sector. I think what we're going to do is we can just create a file buffer straight away, which is a buffer.allocate. We need to allocate for entry.file size. We just want to have exactly that number of bytes, and then in the end we're going to return this file buffer. That's going to be full of the data that we want. So let's do it like this. We can have a for loop, and we can say this is going to be a, what's going to be the easiest way of doing this? Yeah, let's just do it like per cluster. So let cluster equal, and it's going to be like cluster number, right? Not actually like the address of a cluster, because we don't need to do that specifically. The current cluster is going to be start at this one. So we're going to start at 0, and while cluster number is less than the number of clusters that we have, cluster number plus plus. So, alright, so now we can go over each cluster, and what we can actually do is go over each sector in each cluster. So for let's sector, and I guess we don't need the sector offset out here, right? Because sector offset can start at 0, while sector offset is less than this dot sectors per cluster, sector offset plus plus. It's the same thing as the directory entry all over again. So in each of these cases, we can actually get the block of data that we're interested in. And I want to keep track of, let's just keep track of how many bytes are written. This is probably not the best way of doing this, but or bytes read rather. Like, there are different ways you could do this. We could actually just do this on a byte basis and kind of keep track of these things separately, but I'm gonna do it like this for now. So let's keep track of the number of bytes we've read. We're going to want to await. We need an async if we're going to await. So we're going to want to await this dot block device dot read block, and that's going to be this dot. That's going to be this dot. What is it? Cluster to LBA. So we want to convert this to a block number, a sector number. So cluster, and we're going to add our sector offset to that. Alright, so that gives us the block, and we can immediately like put the data that we got from that block into our file buffer. So let's do it like this. We can do block.copy, and we're going to copy into the file buffer. We're going to start writing at the how do we do that? This target start number, so that's just going to be bytes read. That's how many bytes we've read so far. And we need to say where we start in the source. That's going to be 0, and where we end. Now the ending part, that's tricky, because like if we get to the very end, like you see here that we use 6.61 clusters or 52.91 sectors. That means that obviously like we didn't fill, like the data ends before the end of the sector, which means we don't want to read all the data in this block, because at the very last one, that's going to be data that like is going to be junk data. We only want to read the valid part. So what we should do is constantly be keeping track of like the number of bytes left. And so we can do that by taking the number of, well, we can say the file, what is it, the entry dot file size minus the number of bytes we've already read. And that's going to give us like how many bytes there are left in general to write. And what we can actually do is we can use that number. Even though that number is going to be bigger than 512, block copy is not going to complain if we say to write more bytes than are in this block. It's not going to try and read off the end of the block or something. So no worries there. All right. I'm sorry. Yeah. I don't really know too much about specifically about hacking things. It's not really I'm more about like hacking in the programming sense. So you're probably not going to find a lot of good hacking information here. But if you go and search, like if you are interested in that kind of stuff, go and search like for like CCC videos. So in YouTube, search like CCC fail overflow, something like that, and what you'll find is presentations by people talking about how they have hacked game consoles and different types of devices, and they go really in depth about the hardware and the exploits that they use. They're actually really good sources of information. I really enjoy those videos, so I think it's a good place to start. You're probably not going to figure out how to pirate video games from there though. All right, so we're going to do that. We need to update the number of bytes we've read. Bytes read plus equals 512. We're always reading 512 bytes. We could say block.length, but it's just 512. It doesn't matter. Okay, so when we move over a sector, when we move through all the sectors, we actually need to update our cluster number, and that's when we need to go to the FAT. So that's actually... yeah, this is going to be the first time we need to go and look in the FAT. And we need to do a bit of math here, right? Because, so the FAT is, well, it's like anything. It's a block. So it's 512 bytes. And every entry inside the FAT is 4 bytes. So we need to divide that by 4. That gives us 128 entries in every FAT. So if we have a cluster number that is greater than 128, or is 128 or greater, that's going to mean that we actually need to cross a boundary. So we can figure out which boundary we're going to cross. So let's pick arbitrarily. Let's say our cluster number. Let's say we have a cluster number which is like 351 or 352, right? In order for us to get like like the offset in the file allocation table, we need to take the cluster number and we need to divide, or we need to do a modulo. So modulo over 128, right? Because that's how many entries we have in each one. So if we do that, that's going to say that we need to use offset number 96. So we would read a block in the FAT, which would be the FAT begin LBA plus 96. That's the block we want, and then we can actually find the right entry. And obviously then we can't use 352 because now that's like no longer wait, is this accurate? Because I'm thinking now so cluster number and the number of entries in each one is 128, and so if it were greater than that, yeah, this would give us need to think about this for a second. So let's go back to the web browser with the chart, and let's just imagine that each section could actually only accommodate Let's actually make these 4 boxes wide. And let's say each FAT sector is like, so this would be like, instead of having like 128 entries per FAT, we're going to have 4. So this would be 0, 1, 2, 3, and then for the if we had number 4 here, like we would do entry number 4, and that's going to be divided by 4, which is going to give us 1, which is going to say that we use FAT entry 1, and also it's going to tell us that we're reading the first thing here. So that's not quite, no, that's not really going to work. It should work to tell us that yeah, so 0, 4, 5, 6, 7, 8, so this would be 8, and then if we were to do 8 divided by 2, sorry, 8 divided by 4, we would get 2, so this is 0, 1, 2, so this is the page. But then how do we get that offset in the page itself? I think what we need to do there is we need to divide. Wait, I think I'm just getting myself confused here. I think we need to use modulo for the offset. Let's imagine this again. Let's imagine that the cluster number we have is not 350 or something, but the cluster number we have is 9. And let's say that instead of, like, do this situation again where instead of we have 128, we have 4 entries. That tells us we need to use offset 1. So 0, 1, and that's not accurate, but it would be accurate for the position that we would need to look at. So I think I've got myself confused here. What we need to do actually is we need to take cluster number, so cluster number 9, and then we need to divide that by the number of items we have, and then we would round that down. So we would do math.floor, and that gives us the FAT sector offset. And then in order for us to get the entry that we would look at within that FAT, that's going to be using the modulo. So that's going to be doing this. And that's going to say, so we look at FAT offset 2 and we find entry 1 within that table. Yes. // would be the page and % would be the offset. That would be true if we were using Python, but unfortunately there's no / in TypeScript because TypeScript / is a comment. So we need to use floor, or we could also use like some bit shift magic, right? So we could also do something like this. That would also like round it down. But this can have, actually this would work perfectly for this because it's a 32-bit system, so like we would never run into any weird situation there. So the yes, so what we need to do here is we need to say because we need to figure out the FAT, so we should probably read the first FAT entry outside of here and then figure out if we need every time we need to follow to the next thing, we need to figure out if we need to read the FAT again. But the first time we read the FAT, we should read it outside. So let's get, what we'll do is we'll use our global FAT. So we'll say this.fat is gonna, or this.fat sector offset. That's gonna be entry.cluster, and we are going to divide that by 128, and let's just actually make a constant for that. So it's going to be const FAT32 FAT entries per sector, and that's 128. Yeah, so let's use that number instead. FAT32 FAT entries per sector, and then we can read the FAT. So we can say this or await this dot block device dot read block, and it's going to be this dot fat begin LBA plus this dot fat sector offset. What language is this? This is TypeScript. So we get the fat at this point, and then every time we get to the end of a sector and we need to get to the next cluster, what we need to do is to figure out our cluster offset. So we've already done that, and then we need to figure out like where we need to look inside this table. So let's actually do this in the beginning of every loop cycle, because do we do it here? No, let's not do it here because we know we're just reading the file here. Let's do it here, and we don't actually like need to do this thing, so we're going to make this const. We'll call it next fat sector offset. It's going to be this. Yeah, I think what we need to do, next fat sector offset, we're going to compute this, and then what we can actually say is, like, we only need to read this thing if it's different from the current fat sector offset. So if this is not equal to what this already is, then we need to read it. So we'll say it equals this one, and then, damn it, multiple cursors, and then this dot fat is going to be this bot. All right, so every time we get done with that, we can actually like make sure that we have the current like block that is associated with where we need to look in the fat, and then this is going to be the fat cluster entry index. I don't know, this is like a kind of, let's call it fat cluster index. And then what we'll do is we'll take the we don't want to use entry cluster, we want to use cluster there because we're going to change cluster every time. So it's going to be cluster modulo fat entries, FAT32 fat entries per sector. That's going to give us the index, and then to turn that into a byte index, let's actually make this a byte index already, because otherwise it's confusing. This is kind of confusing, right? We have the number, we have the entry in the fat, but every entry is 4 bytes wide, so we need to multiply this by 4 to find where we need to, like, which byte we need to read from. So we'll do it like this. And then we can actually read the next cluster. And so that's just going to be looking at this .fat and then reading a uint32 little endian, and we're going to read that at this byte offset. And now this is the moment where we need to look, and let's go back to this table quickly and get away from my bad diagram. Design of the fat file system. I have about 4 of those open. This is where we need to look and see if we get this marker. So if we get something that's not that well, if we get something that's 0, then it's not going to make sense. So if let's do it like this. If the next cluster is equal to 0, then this doesn't really make sense anymore. So let's just throw an error at that point. The next cluster was 0. Previous is going to be equal to cluster. Yeah, so that one's not really going to work. That's just like kind of an error situation. If the next cluster is greater than or equal to, and it's 0f, ff, ff, f8, so that's our kind of indication that this is like the end, then at that point we can actually just we can break out of this loop. We're done. And it's something that we need to think about is that we could be done before that. So if bytes read is greater than or equal to this, what's going to be entry.file size. Like at this point we're also done. So let's make another done variable. And here we'll set done to true. Whoop. And we will break. That's of course only going to break us out the first loop, so we'll immediately check if we're done, and then we'll break out of this loop as well. But otherwise we'll do all that other stuff, and if we get to the next cluster and we're kind of empty, then we're done. So I think we've actually written this method correctly now. Although I'm certain I've written a bug as well. So let's just check this out. So const file contents. We'll do await FAT32 .read file, and we need to provide that a directory entry. And well, this is actually a valid directory entry. It's not one that we read from, like, you know, well, it's one that we read earlier. We didn't get this through interactions programmatically, but, you know, trust me that it will work. So we're going to read this file, and then we should get that out. It should take a while, right? So I'm going to try and hold the device up to the camera while it runs, so you can see the activity on the bus. And then when it's done, let's just write it out to a file. So let's do await fs.write file, and we'll call it file output. I'm not going to give it an extension, so just file contents. This is, of course, all assuming that this doesn't immediately crash. All right, I'm going to run it. Running. So in the beginning, this is just doing initialization. It's grabbing the FAT, it's grabbing the root directory entry, and it's running now at this point, it should be reading the file. So it's running a bunch of stuff, and I'm going to switch the view. I'm really going to try and be a bit careful with this so it doesn't break in the meantime. You should be able to see some lights flickering. You might not be able to see it because the camera might not be picking it up, but like the green light there, that should be flickering, and that's indicating that there's a bunch of activity going on the bus. And the reason this is slow, well, it's done. We read the 50-something entries. It did. If this works first time, I'll be incredibly happy. So we've got file output, and what do you know? So this is a section of text from the Node.js documentation. Table of contents, a bunch of stuff. It's not interesting, but this is the file, right? Presuming that this, or did we read the same stuff over and over again? I think we ended up reading the same stuff over and over again. And the reason for that is that I never set the cluster to the next cluster, which makes sense. But and the only reason that it doesn't, that we wrote this condition in, so when we eventually get to the number of bytes, that should make sense. So we can fix that. So that's just by saying cluster equals next cluster. All right, there was a bug, but there wasn't a bug that broke everything, so that's pretty good. Let's add some like state in here. No, let's actually not. Let's just do it like this. Okay, so it's running again. Oh, I'm sorry. I'm still on the main view, so you didn't see you didn't see that. Well, yeah, I realized that, and you can see it's running again in the background. I'll show you exactly what I changed. I simply forgot to write this line. So, like when we get to the oh, you also didn't see the file. Apologies, I'm bad at streaming. So I forgot to write this line, and this line is basically saying that when we're done with this, we should actually set the next cluster so that when we go to read it, and is this correct? Because we're going to do the reading here. Yeah, so let's see. It's done now. So let's look at the file, the output. This is looking better. This is looking better. So this is from the Node website. It's the table of contents. So that is the whole table of contents. And then we start getting to the different sections. So we've got like the buffer and blah, blah, blah. And we can see a bunch of example code. So this is just a text file that I wrote to... this is just a text file that I wrote to the SD card. So this is... yeah, this is now working. This is awesome. Yes, so I believe that's pronounced black bytes. Yes, I am writing an SPI driver for, well, I've written the SPI driver for an SD card, and now we're talking to the FAT32 file system layer on top of that, and we are doing it all in TypeScript, so not quite JavaScript, but it is JavaScript. It's going to compile to JavaScript in the end. So yeah, it's confusing. If you want this to make some sense, then you need to go back a couple of streams. Just go onto my channel, take a look at the last couple of streams, and you'll see how this was built up from scratch. This is it. We did it. We read the file. So this is great. This is exactly what I was kind of looking for. And now I want to just like get a little bit like kind of conceptual about the whole thing, because we've kind of covered all the concepts here that we would need to do anything, right? Reading files, but also writing files and deleting files. So if we were going to write a file, right? If we were writing a file, the way we would do that is that we would need to write into some directory, right? We need a place to write. So we would need the user to pass us some kind of directory entry. So let's just write the function signature, right? We would do something like this. We would need, a directory, which would be a directory entry. We would need a file name, which would be a string. And then we would need the data, which would be a buffer in Node. And then what we would do inside this function, basically, and I'm not going to do it now because it will take us ages, and this has already taken a long time to read a file. But what we would do in this case is we would look at the FAT, so the file allocation table, and we would look for the entry, the first entry we find that has a 0, and that 0 is going to tell us that it's a free cluster. So then we're going to have a cluster number that we can start with. And probably what we would do is we would work out how many clusters we need for the data that we have. So we're going to find all of those clusters. We're going to search for, let's say we need 20 clusters. We're going to search through the file allocation table to find 20 free clusters and store them in an array or something like that. And then when we have those clusters, we can actually go and like write the data into those, right? That's just basically converting cluster numbers into block addresses with the offset for the sector and just writing that data in. Exactly the same as how we read it out, so the complete reverse. And then once we've written the data there, what we can actually do is go and update the directory contents to say that there is a file that starts at some cluster number. And so that's going to involve basically opening up that like directory, so finding the directory that represents like this entry, yeah, I guess we would need a directory cluster number. We don't really want to have a directory entry because that wouldn't make sense for the root. I guess we would use the current directory or something like that, so maybe we wouldn't take that. But we would look into the current directory, and we would actually need to look at the current directory in terms of its binary representation in that case. And we would need to find the first entry that has a 0, because that's going to say that, or a 0 or an E5, right? Because that's going to say it's a deleted file or something like that. So if we find one of those, that means we could actually write our file, like our file entry to that place. So we could update that. We would just write that back to the disk. Do the updates, write it to the disk. And then when we've done those two things, then we can go to the file allocation table and go and fill in that big linked list with all of our cluster numbers. And the reason that you do that kind of last is that if you were to mess something up in that moment, like in the file when you're editing the file allocation table, that's kind of the most dangerous step, because if you mess the file allocation table up, you can kind of corrupt the file system. Don't ask me how I know that. I definitely didn't experience that firsthand, messing around with this code. But yeah, you can mess up the whole file system by doing that, and you kind of need to do a format or something like that. So that is how writing a file would work. And if we had a delete file, well, that's even easier. Delete file. And we probably would take a directory entry from that. And I guess we would just delete an entry. We wouldn't delete a file, because we could delete directories as well. So to delete a directory or an entry or something like that, what we basically need to do is take the current directory that we're in and like the entry that we're looking at, and we need to just set the first byte to E5, because that all we do there is that means that is like it's a deleted file, it's no longer there. So if we did that, like that would kind of be a first stage deletion. That's the fastest way to delete files. And in fact, that is what like very early versions of Windows and things like that did. And that's what many things still do today. They just write that first byte as E5, because that means you don't need to do more work. You literally just need to write one block and you're ready to go. But at some point you need to go and clean up the file allocation table, because this file still might have links in the file allocation table. So what if you really, really want to delete a file, what you would do is you would go and erase, actually you should do this anyway, right? But you should go and erase and set to 0 all of those cluster numbers that are involved with that file. But notice you don't need to go and delete the contents of that file on the disk, right? You don't need to go and find all of those clusters and sectors and like zero them out, because you're removing the information about where those files are, like from the lookup table. You're basically, as far as the drive is concerned, like it's going to find a free entry and maybe go and overwrite that data later. But this is why you can recover things like photos and stuff like that from SD cards and other drives and hard drives and things like that, because most of the time when you delete files, you only delete the metadata about the file. You only basically mark it as free. You don't need to get rid of the actual data on the drive itself. So this is why like you can go and find old like recovered stuff from these kind of drives. So that is pretty much it. I'm not sure if I'm going to do more videos in this FAT32 series itself, or the SD card part, because I feel like we've kind of, like anything else is just going to be tuning it up and making it nicer and kind of writing these nice APIs like, maybe like change directory and then setting a path here and having the path be a string and like kind of doing all of that kind of stuff. And like that is interesting, but we'll see. Maybe I'll do it next week, but I might switch gears next week and take on a different kind of topic, and that might be doing some bus pirate stuff, and it might be writing a driver stack for another device that I have, which is even more powerful than the bus pirate, but is going to require some more advanced stuff, and I don't know too much about exactly what I need to do with it yet, so we'll see. Alright, okay, so at this point I'm going to take a look at the chat, and if you guys have any questions or anything that you want answered in this last couple of minutes, just throw them in the chat and I'll try to answer them if I can. So I'm just going to catch up with it for a second. So I see here, great job, it worked first try. Didn't quite work first try, but almost. Does this handle fragmented files too? yes, this does handle fragmented files, because the cluster number, so fragmentation in the context of FAT32 and these kind of file systems basically means that your data starts getting like spread out all over the disk in different places. So it's not like written all nicely next to each other. All the files at the moment, they're all contiguous. So every cluster is next to the previous cluster. But once you start deleting files and things like that, the operating system or the driver or whatever can actually start selecting old clusters and using those instead. And what that means is that now, you might pick a cluster here, and then there might be a load of stuff in the middle that's unrelated, and then you have the next cluster is like 100 clusters away. And then that's fragmentation, because now your data is like spread across the disk. It will handle this though, because we're just looking at the cluster numbers and we're following the links in the file allocation table. So we'll happily jump to we'll happily jump from this place in the file allocation table to this place and read to the next block, even if it's super far away. It doesn't make a difference to us. It gets a bit more complicated when you're writing files, because then you need to do a lot more work. You have to really look in a lot of places, and maybe you need to scan through the FAT and multiple sectors and things like that. Yeah, fragmentation's a problem, and that's why in Windows and old school Windows you had to do defragmentation every now and again, which would go in and rewrite the FAT and move things around so that your files were closer together and more contiguous and made more sense. Alright, so George B says the series is so good at showing how computer software is just layers of complexity and abstraction on top of layers of abstraction. In the past, I would have assumed that something like the file system is probably so baffling as to basically be magic, but it's really not that complicated when you look at it from the ground up. Yeah, I'm really super glad that that's kind of the takeaway that you come away with, George, because that is exactly what I'm going for not just in this series, but kind of the whole thing on the channel is these concepts. Every complicated concept is really just, if you chop it up, is a bunch of small, not that complicated concepts. All of the concepts within this are all pretty simple. It's only once you start building them up on top of each other that things get a bit complicated. And of course, by the time that you've built a couple of levels of driver stack and you're building a file system and someone just walks in the middle of that, then that maybe looks like it's really complicated. But actually, you've just done all the little simple steps to get to that point. All right. At least the FAT is simple, ext3 is scary, and so is NTFS. Yeah, okay, so that's true. Also, the FAT file system is a simple file system. So it's the reason that things like SD cards and things like that pick it is because normally when you take an SD card, you plug it into an embedded system. For instance, I have a 3D printer over there, and there is a port where you can plug in an SD card, and there's no computer inside that thing. There is a circuit board with a microcontroller, and that microcontroller needs to be able to figure out the file system. So the file system can't be too complicated. It has to be doable within, a microcontroller, which might have other jobs in the system as well. Okay, so they say that 1 is the loneliest number, but they've never met a dereference cluster. Yeah, that's a nice one. Although in the LBA formula, so the cluster to LBA method that we wrote, if we plugged in cluster, and so if we plugged in anything but 2 here, we're gonna get stuff that just makes no sense at all. So you're completely right. So people here are talking about file systems, and someone says, "Hi, I'm new. What are you doing right now?" Well, we're just finishing up with some file system stuff, so I guess you're gonna have to take a look at the stream replay in order to see what we've covered. But that's about it. I'm thinking yeah, I'm thinking about how I'm gonna what kind of videos I'm gonna do from here, like in these streams, and I might actually be revisiting the RISC-V series, because that's a series that in my mind is still ongoing. Some people have asked me if it's still happening, and it's absolutely still happening. And that one's a nice one because we're building very slowly, but we're building a RISC-V CPU using the TypeScript programming language that will run on an FPGA. And so this is an FPGA board. It's an I need to maybe move that closer and then bring it out a bit. This is an FPGA board, which is an RT-A7, and it's got an RTX 7 chip here on that. That's an FPGA. And using some infrastructure that I've written over the years, we can actually like write hardware for that in TypeScript. And so that's something that I would like to continue with, and maybe I've been doing it in videos so far, but I might actually just make those same kind of videos but do them as streams, because at the moment I have some some other obligations and things happening in my life that means that I can't dedicate as much time to making the videos themselves. But the streams make some sense because I can just pick them up one evening in the weekend, and that works really well for me right now. RISC-V disassembler would be good. Yeah, it's that would be a nice project indeed, and it's something that we might do. I mean, at the moment I have the RISC-V tools installed on my laptop, so it's easy just to do disassembly like that, and yeah, throw in code from the RISC-V tools and things like that. But it would be nice to do indeed. Hello from Brazil. Come to Brazil. I do have some Brazilian friends actually. Some of my colleagues, well, at my old company, some of my colleagues there were Brazilian, and they're all really nice. None of them live in Brazil anymore. Well, some of them do actually. Some of them were remote. But yeah, I would love to go to Brazil. It's a beautiful place. It looks like a beautiful place. Would like to see some more stuff that makes use of the Salier. Oh, that's a great one. That is another idea that I have for a project, and that would be taking some kind of like SPI peripheral or an I2C peripheral, and like writing some code for it on an Arduino or on a microcontroller, and like kind of using just a library there, right? So kind of, I've actually got some like temperature and humidity and kind of different kinds of sensors like that. So they might actually make a good use case for that. And what I was thinking is I would write a program in an Arduino or something like that that's like reading from this sensor, or maybe an accelerometer or something like that. And then what we could do is we could hook up the Salier, and we could reverse engineer just based on the high level code. Like we could almost treat it like a black box. Like we don't even know what the code is. Obviously I need to know what the code is because I'm going to write it. But we could treat the device as a black box. We could sniff the signals using the Salier. And then we could reverse engineer it and write a driver using the bus pirate and see if we can get something that works the same. I think that would be a really fun project to do on stream. Especially if I don't look at the details ahead of time, because then I could really do the reverse engineering and yeah, take hours and make mistakes and stuff like that, which is more fun to see in a stream than it would be in a video. French are here. Hi French. What was your first programming language, and what programming language do you recommend for a beginner? My first programming language was probably, I mean, I'm going to say it was probably just like HTML and some JavaScript. I used to go to I didn't have a computer at home, but there was a library that was like literally a couple of like 1 minute down the road from where I lived as a kid. And they had a couple of computers in there, and you could go and reserve a computer. So I did that every day. I would like reserve a computer after school in the library, and you could only reserve for like an hour, but I would like I would reserve the maximum amount of time that I could in the library on the computers. I had a stack of floppy disks, and I would go in there and I would basically make GeoCities websites. And I had no idea what I was doing, but I was like looking at all these websites back then and like finding snippets of HTML and just figuring stuff out. And yeah, so probably in some way my first language was probably JavaScript, even though at that point I had no idea how it worked, and I was just pasting bits of magic code into my stuff to pop up alert boxes and things like that. I had no idea what I was doing. That stuff only came later. And then the first language that I really properly learned, like got into, is arguably something like Quick Basic, but probably Visual Basic. VisualBasic.net. Yeah, my dad, he bought me, at the time you had to buy this software and it came on a CD-ROM drive. So my dad bought me this VisualBasic.net CD, and this was about 1 year before they started giving it away for free, and then you could just download it. But then I got really into it and I bought a load of books and I learned VB.net. And then from VB.net I learned C#, and then I learned a bunch of languages from there. Which language do I recommend for a beginner? I think JavaScript and TypeScript are good languages for beginners because there's tons and tons and tons of resources online, and it's super easy to make something like run in the browser and just see it working. So maybe that. Maybe Python, because Python's an easy language as well. Yeah, I don't believe in these like people that say that you should learn C and things like that as your first language. Like, just learn C later when you already understand programming a bit, because otherwise it's just unnecessary like details and tricky stuff that you have to come to terms with. Probably Python is the first best language to learn as a beginner. Did you try to make a game in JS? Yeah, I've made a bunch of games in JS. Yeah, it's one of my first jobs, actually. The first job I got out of university, and I studied game design at university, so I actually made a bunch of games, not in JavaScript, but in other languages. And the first job that I got out of university was working for a company that made device simulations, but in gamified form. And the first thing I did for them was to make a game engine for their new generation of trainings, because they had written everything in their old generation of trainings in Flash, and they needed to move from Flash, which was dying, to HTML5 JavaScript. So that was my first job, and I did that for a couple of years. Do you have any video on video games in JavaScript? I actually do have I mean, not on building video games specifically, but I did make one video about starting to build up a game engine in JavaScript. Yeah, you'll find that on my channel somewhere. It's in the one-offs playlist because I didn't make a follow-up video to it in time. But yeah, you'll find that on the channel. It's pretty specific. It's to making like sort of like retro-looking text games. But it does actually use like modern techniques with the canvas and drawing stuff. So hell yeah, GeoCities style websites is the way to start. It's a shame now that, I mean, maybe these things do exist, but it's a shame now to think that, like, I think it's not as easy on the web today for kids to like pick up stuff like that and just do it. Like, it was such a different kind of web when I started programming. It's so much better now though, right? Because the information is like, there's so much more information, and YouTube has tons and tons of stuff. You can learn anything on YouTube. So if you want to learn some obscure programming language, I remember like when I was a kid, I found a book in the library that was about Unix, and I'd only ever used Windows computers, and I had no idea what Unix was, but I got this book from the library and I was reading it, and I was just so confused because I didn't understand, like I saw them writing commands, and I was trying to type these commands into like the command prompt, and they weren't working, and I was just like, well, this is stupid. But I just didn't understand what Unix was until a couple of years later when I finally found a Linux bootable CD. Um, can you do can you do Streets of Rage in JavaScript? Because I found one Pygame, but not JavaScript. I'm not sure if I could do that specific thing. I didn't actually. I think Streets of Rage. I think that was a Sega game, and I was like a Super Nintendo person. I guess I was more like a Nintendo 64 person, but so I probably couldn't make that exact game, but maybe I think Streets of Rage is like a beat 'em up, like side-scrolling beat 'em up kind of game. I did actually always want to make one of those kind of games, but I'm not sure. The thing is, games take so much. They take so much time and effort, and you really have to write a lot of code to make a game, and it's just a long-term project, and I have so many long-term projects on this channel already that are like in various stages of completion, that like the idea of starting a new long-term project at this point is kind of like yeah it's kind of a barrier that I would have to overcome. Could take the script and improve it. I think if it was a Pygame, it was like porting a Pygame thing is going to be quite a lot of effort as well, just because first you need to port the entire Pygame. Well, one thing you could do probably is, I imagine at this point that someone has made a WebAssembly like binary version of Python, and probably we could shim it together so that we could actually run the Pygame stuff and just like map all of the drawing SDL commands to the canvas. That would be an interesting experiment, and that actually might be something that I would be more up for, because we wouldn't have to do the whole game development, but also we could explore something interesting, which is like getting into WebAssembly and writing kind of like the backend shim stuff for WebAssembly that you need to do. Like, right, if we're like trying to call out to SDL, we can intercept that and turn it into canvas stuff. So that's something that could be interesting. I would be interested in doing that. All right, I think I'm gonna have to. Call it an end of stream at this point. I really want to thank everyone for joining today and just like enjoying the general file system hacking stuff. This is really fun. I really enjoy doing this. I especially enjoy mixing the hardware side with the low level JavaScript side. It's like they're the two things that make me the happiest. So I'm really glad that there are a bunch of people out there that enjoy this stuff as well. And yeah, have a great weekend, everyone, or the rest of the weekend at least. And I'll catch you next time.